I'm here to talk, or we're here to talk about this PTMApp, the most unimaginative acronyms in the world. And I have to take credit for that, but I'm going to step through and kind of talk to you about this thing that is PTMApp. You know, when I give or I discuss it with people, everybody's heard of it, and you know, it's another tool in the toolbox. And nobody really understands it. And it's hard, even in an hour, to convey what this thing can do and but we're going to try. There we go. So what we're trying to do is fulfill a Bowser, or the Board of Water and Soil Resources business need here. And really, you know, what Bowser's trying to do is to demonstrate that clean water dollars that are going to local governments and projects are prioritized, targeted, and capable of producing measurable results. Okay, so that's the PTM and the PTMApp, and that's again, I apologize for the unimaginative acronym, but PTM is fundamental to the One Watershed plan, and it's a key concept in nonprofit priority funding plan. It's not a new concept. It is an extension of the RAPs. You know, we've been talking for years, those of us in Minnesota, and I know the legislature has been talking years about justification, uniform approach, a means to quantify practice performance, support clean water fund applications, estimate benefits of regional statewide projects, and we wanted to make something that's usable by local government. So what I'm going to do is I'm going to start by just telling you a little bit about where this came from, because I think it's important to set up a context of how we got here and where this came from. Excuse me. As far as your 10-year cycle, I could make an argument that PTMApp applies to each one of these items in this pinfield. We're going to focus kind of on the last three, but in the One Watershed One pilots where this has been utilized, we have used it for each of the 5 components of your 10-year cycle. So what I'm going to talk about, or what I'm going to do today, is the first 2, and then I'm going to turn it over to Mark and then Henry. But really, I want to talk again about the evolution, how we got here, because it's important for people to understand where we came from and how we got here. So I'll just kind of talk a little bit about very basics about what this PTMApp is, at least you know how this thing is put together. Then there'll be some validation discussion, you know, some of the theory behind what we did. And then we'll talk about some examples, and then some final thoughts. So, for those of you who don't know the International Water Institute, it's a nonprofit organization. I work in the Red River Basin. It's a small nonprofit. Besides me, there are 7 other employees. The organization is focused on watershed research and watershed education. So, who's heard of Riverwatch? Great. Riverwatch is one of our signature programs that we deliver, and a number of other things. But there are really, other than the Riverwatch staff, there are 2 of us that work in this watershed research or watershed information side of the organization, and that's myself and Britt May, who is my GIS technician. And so when I talk about PTMApp and I talk about what the Institute does and how we're involved in this, it comes down to decision support. That's really what the role of the Institute is with watershed districts in the Red River Basin, soil and water conservation districts in the Red River Basin. It's about decision support. And my concept or my definition of decision support may be different than what you think. To me, it's simple. I'm here to provide information to a customer. That's it. And my job is to package that information, and it could be old information or new information, but it's good information so they can make better, more informed decisions. Simple, right? So I have to start this talk, when we're going to talk about PTMApp, I have to go back, because what we're talking about here and what you're going to hear about is a gridded-based approach. Okay? And I know there's a wide range of audience here and a wide range of understandings, but I can't walk into a room like this and look at ceiling tiles and not think of a gridded-based approach. Now, those of you who are laughing, you get it. Those of you who are looking at me like, what is he talking about? Don't. and hopefully as we go through this presentation, that will become clear. So it started in 2005. And really it started, actually I could go back to almost back to 2000, but after the 1997 flood in the Red River Basin, we had a great need for elevation data, better elevation data. My organization and I was the one that basically spearheaded the Red River Basin Mapping Initiative that resulted in the Red River Basin LiDAR collect. At the time, it was the largest LiDAR collect that I know of in the U.S. Actually, I think anywhere in the world. We collected 54,000 square miles of LiDAR data in the U.S., on the North Dakota and the Minnesota side. And when I was working on that project, both from selling it to local units of government, federal and state governments, but as we were I wanted that data. And to me, the data was an end to a means. Sean talked a little bit about LiDAR yesterday. LiDAR data is one thing. It is not the end, right? I always had this vision that LiDAR data was going to give me something that I could do all these wonderful things. And there are some wonderful things that we've done with LiDAR. But once we got the LiDAR data, we started to play with terrain analysis. And I mean, our work with terrain analysis, we've been doing this for well over 10 years. I mean, between Brittany in my office, the other partners that we work with in the Red River Basin, Henry VanOffelen, Peter Mead, others, I mean, there are some talented GIS people out in the Red River Basin. And they work very well together to develop these concepts and apply these terrain analysis techniques to develop this information that we're going to show you today. So the funding, of course, for the Red River Basin Mapping Initiative, there are 15. But this is a public investment. Everything we're going to do here, from the LiDAR project, the terrain analysis, once we had the LiDAR data, we did something we call Watershed planning tools, which help local practitioners develop flood damage reduction scenarios, develop projects, go through the permitting process. But they're all online tools. And the important thing here for the Institute, and this goes back to my very first chair, who was George Sinner, former governor of North Dakota, my goal is to build something that local people can use, okay? So LiDAR data is an incredibly complex and technical thing. I mean, if you don't understand it, the goal that I had was to build something that everybody could access it. That was the promise that I make. Everything that I do, I always make a promise to my local folks. When I'm done, you'll be able to use it. You'll be able to access information. You will not have to call your consultant and pay them to get you the information. That is the role of the Institute. Everything we've done, everything we're going to show you, and everything the Institute has done, that's been the end game. I built something that locals can use, okay? So this really, after we did the Watershed Planning Tool, we developed this thing called the Water Quality Decision Support System, and that was kind of the foundation, or the first thing that resulted in this PTMApp. And I'm not going to go into what these things are, but there's been a considerable public investment here, and not so much a state investment. I mean, this has been local dollars that have been spent on this, many hundreds of thousands of dollars, mostly from the Red River Watershed Management Board, to do these things, okay? So again, remember, grid analysis. So when Mark and Henry are talking, think of the ceiling tiles. Okay, so as a part of the PTMApp process, and I'm going to have to hurry here, we were trying to address local goals. Again, everything we do has a customer, and my goal is to give that customer what they need. So we work with Doug Thomas and Melissa. We have formed something called a Blue Ribbon Panel. We kind of invited SWC folks from across the state to come together and help us to figure out what it is that we were going to create, to help them do their work. And their work comes down to implementing. It's trying to get work done on the ground so they can so we can address the resource issues that are out there. So the first goal, of course, that we got from this Blue Ribbon Panel is they wanted information. And they wanted information that local practitioners can use. They wanted to provide a source of information to identify and agree on priority resources in their area that they're working. Excuse me. And then again, it goes back to implementation. Everything we're doing is trying to get to their work plan to implement projects. And the last one is the most important, and I hear this time and time again. I don't want to have to pay consultants all the time. Okay? Mark, he loves it when I do this all the time. But again, the goal here is to get a product that at the end of the day, I don't have to call a consultant. That's the goal, right? And so we do this all the time, everything we do. So this is what we heard from our Blue Ribbon Panel. We went through this process where we created products and gave it to them and said, tell us, does this make sense to you? Can you understand it? And is there value? Okay, so everything we're going to show you, we went through this process of giving them these products and saying, does this work for you? Does this make sense? And we got feedback from them, okay? That's how we created this. PTMApp in itself consists of two pieces. There's a desktop component and there's a web component, okay? That's it. There's two pieces. The idea here is that the desktop component, yes, you need somebody who has GIS knowledge to be able to create the data product. Once those data products are created, they're uploaded to a server, and then through the web access, anybody can access that data. Now, it's not for public consumption because there are some sensitivity issues here because we're talking about a very fine grid scale, 3 to 5 meters. And one thing we heard from the Blue Ribbon panel is, it's not information that we want to share with the public. We don't want anybody access. So you have to be able to log on and register, and there's some administrative controls as to who can see the data and who can upload it. Okay? The desktop is actually an ArcGIS toolbar. You load it into your ArcGIS. There's, I think, 11 modules. You can go ahead, you run it in your ArcGIS, and it creates a database. And I'm not going to get into this, but that database comes with prepackaged data. There are input data that we need. These are the input data that we need. Sean talked a little bit about some of these, but there's a plan boundary. What is your area of interest? You have to be able to identify what your priorities are. The priority could be a reach, a lake, could be anything. But remember, this is water quality, so we have to say, hey, I got an issue here. I want to protect here. I have a sediment problem here. And you actually have that point data that point or polygon data that's a part of your plan boundary. The travel time, curve numbers, elevation products. Of course, there's DEM, circle soils, the Russell inputs, and then there's this hydro condition DEM that Sean talked about yesterday, an important piece of this. In the Red River Basin, we've been conditioning DEMs for over 10 years. And I know that when I talk about, and I know Sean too, when we talk about conditioning or hydro conditioning DEM, people seem to get these weird looks in their head, and they thought, oh my God, that's hydro conditioning a DEM is incredibly easy. It's not a difficult process, but it's incredibly repetitive and it's mundane. I have 5 interns now working on hydro conditioning a DEM, and I can tell you that the best of them can do it for about 4 hours before they go goggle-eyed and have to step away their computer. Okay, but it's not difficult. Okay, that's the important thing. So we've developed this matrix, or actually Mark and Houston did. This is actually a matrix of the various hydro conditionings that you can do. We focus in the Red River Basin on everything we do. We kind of try to push things over here. But PTMApp will use any condition DEM you have. It doesn't matter. Okay? But again, the conditioning is a result of what your business need is. So the web, again, I said you need a user account, and again, currently only local users can access that. So I'm going to turn it over to Mark now. He's going to do the validation results, and then Henry's going to show some examples also of data products in the Red River Basin.
He said he was going to talk 10 minutes. That's Chuck. Thanks, Chuck. PTMApp is for planning. Did everyone hear that? PTMApp is for planning, water quality planning. One last time, what is PTMApp for? Water quality planning. Okay, so if you don't remember anything else from today, remember that. I do want to acknowledge my colleague, Dr. Drew Kessler. He's in the back of the room there. He's been very involved in this, and it's been fun to work on this project along with Chuck on behalf of the Red Board and the folks in the basin. So I'm going to talk a little bit about validation. I'm going to try to get through some examples and show those to you, and then leave you with some closing thoughts. So one of the things that is important is trying to make sure that the results we get from PTMApp are reasonable. And that's how I'm defining validation in this particular case. We've done to this point in time only limited validation. Most of that has been within the Root River watershed. And when I say validation, what we're doing is we're checking the annual loads and the annual yields from this product, the geospatial products we're creating, and basically making sure they're reasonable. Now that's not the same term that a classic modeler would use as a guy coming out of St. Anthony Falls lab. You would say first you're going to calibrate the model, and then you're going to validate it or verify it. But we have done some work on validation. As most of you know, there's some challenges anytime you check any model, anytime you calibrate any model. What you're doing is trying to make sure that what the products coming out of it or the results match the real world. One of the biggest challenges we have in any validation is that in PTMApp we're actually getting information about sediment, suspended sediment loads, and yields. Most of our monitoring data is as solids. So when I show you validation results, what you have to realize is I've manipulated some of that monitoring data to get it into the same language that I can use to then compare to the PTMApp results. The validation results, again, we've only done this for the Root River so far. We are checking other areas. We're using some of the Sparrow results. PTA has been kind enough to send those to us. So far, within the Root River, what we've learned is that the results are reasonable, at least for sediment. Now, reasonable at what scale is always a question. We've basically checked the results in terms of the loads and yields at the edge of field scale using the field to stream partnership data. We've also checked it at the small watershed scale, meaning roughly 1 to 2 square miles in size. And then we've checked it at the large watershed scale. The Root River is very large. We've matched up or looked at yields and loads up to about 1,500 square miles in size. When I say the sediment results are reasonable, that means that when we compare it to the monitoring data that we've converted to suspended sediments, that generally we're within about 40% of the measured values. You probably ask yourself, how could that be reasonable? You're basically telling me you're 60% off. Well, the reality is what PTMApp does is it's predicting or estimating the amount of sediment, in this case, from wash loads, using a landscape from the field. As you all know in the room, there's another component to that. That's the near channel sources. And recent work by Dr. Belmont from Utah State shows that the near channel sources in the Root River can be as much as 40 to 80%. So that's how I got to the results are reasonable. The phosphorus, the total nitrogen, and the total phosphorus loads and yields seem reasonable at the field scale, edge of field scale, and at the small watershed scale. What we've learned is that they're off at the large watershed scale, and the reason is that some of the parameters in the model, which you can adjust, or within the application, I should say, probably need to be adjusted a bit. We're basically under-predicting in some cases those nutrient loads at a large watershed scale. Another way to check the results is through comparing information on a relative rank. We did this early when the IWI was developing the Water Quality Decision Support application. What I'm showing you here on the screen is the Sandhill River watershed in the northwest part of the state. The black lines are the sub-watershed boundaries. Those are 12-digit hydrologic unit code boundaries, so that means they're roughly 40 square miles and up to, 160 square miles in size. This is sediment yield, but we've converted it to a rank, okay? And the question is, if you're going to do a source assessment, you want to identify where practices should go on the landscape. Are we generally able to identify where the largest magnitude of that sediment is coming from? So the areas in yellow, and this is contribution to the outlet on the far upper left-hand side of the graphic, the yellow areas are the areas with the highest contribution of sediment actually reaching the terminus of the watershed, or in this case, the Red River of the North. Again, what we did is, do we have a matchup? In other words, the lower graph is the HSPF results. The upper graph is the results from the Water Quality DSA. And we have, in my opinion, general agreement. The reason I say we have general agreement, because me being me, I ran a statistical test on it, did a chi-square, and found out there was no statistical difference in terms of the ranks coming out of these two applications. You shouldn't expect a difference because in both cases, those models were actually calibrated. I hate this when we do this. I'm going to spend a little bit of time talking about theory, hopefully. How many people in the room are water quality modelers? Raise your hand. How many people use model results? Most everybody, okay. So what I'm going to do is I'm going to try to do a high-level overview of the theory. If you want to know the details of the theory, there's 4 technical memoranda on the PTMApp website. You can download those and you can look at the theory. You can make your own judgment about whether what we're doing is technically defensible or not. We welcome the discussion. That's what science is about. In terms of the water quality, what we're doing is really fairly simple. We're estimating total phosphorus, total nitrogen, and suspended sediment loads and yields on an annual average basis. In terms of how we come up with the sediment numbers, we're using the revised universal soil loss equation. Nothing fancy. Do people know that that same equation is the genesis basically of SWOT and other models? So we're really not doing anything different than anywhere else. Okay, I want to make that point. In terms of the nutrients, total phosphorus and total nitrogen, we're using simple land use based coefficients, export coefficients. Again, nothing too fancy. Those export coefficients essentially come from monitoring data. Okay? Then we're doing that computation, as Chuck said, based on the ceiling or hydro-modified DEM. We're actually doing it on a raster scale, so we're making an estimate of the loads and yields for every 3 meter by 3 meter space on the earth within the watershed. And then what we're doing is we're keeping track of where that mass goes. We're basically routing that mass downstream using some simple equations. They're first order decay equations if you really want to know what those equations are. Again, that's a very commonly used approach in the water quality modeling world. We track that mass downstream to user-defined locations. So basically when you run PTMApp desktop, you put points in it, and those are the locations where you're able to get information about loads and yields and the effectiveness of practices. You can scale the results. So one of the features we built into this is if you have real monitoring data, you can actually tweak the results in PTMApp to make sure you match those annual loads and yields that you monitor. Basic, quote-unquote, calibration steps. So if you have data, you can do that. If you have a SWOT model or you have HSPF model that's been calibrated, you can tweak the results or adjust the results if you wish to meet that. Why would you do that? Maybe you had an HSPF model or a SWOT model that was used as the basis for the TMDL equation, and you want to make sure that you're matching the loads. That would be a reason that you would want to do that. The data that you get out of this, I like to think of the data as enhanced geospatial water quality products. Okay, but you get that information at multiple scales. The raster scale, again, that 3 meter by 3 meter cell on the base of the landscape, as Sean was calling it yesterday. At the catchment scale, we define catchments basically as fields. I'll show you that in just a bit. But generally areas in the watershed that are roughly 40 acres in size. Sub-watersheds, those areas where you put points in the model and you want to get results at a little bit larger scale, and then the entire watershed. We can't do bacteria work, but Drew's a really smart guy and he's working on that. So it is a matter of scale. I want to reinforce what Sean talked about yesterday about the importance of scale when you're addressing a problem. What I'm showing you here on the screen is the catchment size. So these rose-colored boundaries, hopefully you can see them. It's a little bit challenging to see, apologize for that. Those rose-colored boundaries are the catchment boundaries. Those are portions of the watershed where we're keeping track of this information. Even though we calculate it at this very fine scale, generally we summarize it at what's called the catchment scale or the field scale. So I want to talk a little bit more about scale. What I'm showing you here is a graph of HSPF results from Lake of the Woods drainage area, work that was done as part of the RAPS. The computational element in HSPF, I'm sure you heard yesterday from Chuck Regan, is what's called a per land or an imper land. That's what's shown on the left-hand side of this graphic. Those different colored areas are different amounts of sediment coming off the landscape at the per land scale. Looks like a raster almost, right? But the difference here is that within HSPF, we don't really get any information spatially about whether that amount varies. In fact, the yield off those purlins is constant within a climate zone. But we can still take that information, we can still upscale it, add it up essentially to a larger water scale and use that information to make water quality decisions. And that's what I'm showing you on the right. What we've done then is reported that information at the sub-watershed scale, again, essentially at the 12-digit HUC scale. On the right-hand side, what I'm showing you again is sediment yields at roughly a 12-digit HUC scale coming off the landscape from the HSPF model. Still a very valuable product. You can use this, again, to do source assessment. You can use this to target where you might put practices. So how does that compare to PTMApp? Remember that I said we're doing the calculation in PTMApp at this very fine scale. You could maybe argue that we're doing it at too fine of a scale when you look at all the input data. But that's what I'm showing you here on the left then is that raster scale, roughly the same size image. But I'm showing you here the sediment yields, in this case they're ranked, but again, leaving the landscape south of Lake of the Woods. And then on the right, I'm showing you that we've accumulated those or added those up to the catchment scale. So that's one of the fundamental differences of what we're trying to do is we're really trying to push that data to the field scale. Why do we want to do that? Because ultimately we want to engage landowners in a discussion about what is happening on their land and practices to place on the land And if you're a landowner, you want to know the benefits of that. So if you're a farmer, he's going to ask you, well, if I do this, what good is it going to do in the real world? What good is it really going to do in the environment? So that's what we're trying to get to here. And finishing the discussion of scale, what I'm showing you here is one of the products from PTMApp. Again, Chuck mentioned to you that we're using this raster, we're using this fine scale. That's what I'm showing you here on the left-hand side. In this case, this is the results from the universal soil loss equation computed at that 3-meter scale. But what we also keep track of, as I already mentioned, in PTMApp is where does that mass go once it leaves the landscape. One of the first things we do is estimate the amount that actually hits a flow line, actually hits a gully or a channel or some sort of water feature in the field. And that's why the graph on the right-hand side differs. Those gray areas that you see peeking through on the right-hand side are areas where sediment has left the landscape but never made it to the waterway, never made it to the flow line. So again, if you're a local practitioner working with a farmer, it helps you identify what you should do in the landscape, where you might want to put practices. Once we calculate the information or estimate that information at that fine scale, the products that we're generating, these enhanced geospatial products, we keep track of it at that catchment scale, at that field scale. And so what I'm showing you here is a portion of the Red Lake River up in the northwest area. In fact, I'm showing you the most downstream location. And because we're tracking that mass, we're able to identify how much of that sediment, phosphorus, or nitrogen mass that actually makes it to the outlet. In this case, why would you care about that? Because normally you're not managing locally for the water quality. You're managing to some point downstream. In a paired lake, a lake you're trying to protect, in a paired stream reach, something else further downstream. So the value of tracking this is that we get better sense of if we do something in one part of the landscape, where are we actually going to realize benefits from that? And so this is the same information but at a different scale. So now I'm showing you the catchment data sediment leaving the landscape that actually reaches the pour point. The darker blue areas are the areas with more contribution of sediment at the pour point, which is, I'll mess this up, which is here. Here's the pour point for the watershed. Why are they all blue near the outlet? It's not rocket science, folks. Those catchments are closest to the outlet. The other thing I want to stress, though, is what do you see on that graphic? You see these red blobs. Those are the points that Chuck mentioned that when you're creating the data in PTMApp, you can give the application locations where you want information. It's basically just a point shapefile. So you can then generate this same type of data, not only for each one of those points, but cumulatively downstream. So it's important that if you're going to use this tool, you think about where you want information. Those red points typically, again, could represent anything. It could represent you want information about a load to an unstable stream reach, you have an impaired stream reach there, you have a lake there, whatever. But the user defines those locations. Hydrology. We do hydrology in PTMApp. It's not very sexy yet. We're trying to make it better. But basically it builds off, I'm going to use Sean's term, the hydromodified DEM. We take that flow accumulation raster and the flow direction raster that Sean was talking about yesterday. It goes into PTMApp and we create these catchments. You can right now enter user-defined precipitation depths. Typically by default we use 2 and 10 year, and the reason that we use that is because from a water quality practitioner's perspective, those are the kinds of precip events that are of most interest to us. We use those to size practices in the field typically. Again, the computational scale for the volumes is the raster, for the peak discharge is a catchment. It uses curve number abstraction, so basically the amount of water that goes into the ground by infiltration is through using the curve number approach. Peak discharges are computed using the SCS unit hydrograph method. So I'm going to have to not explain those here. If you don't know what those are, I apologize, but again, we can maybe have a chat later. As before, you get the data at the same scale. The raster, the catchment, the subwatershed, those red points, and the watershed, the outlet of the watershed. We are working on improving the hydrology. I'm using Clark unit method and doing some linear storage routing as well. So this is a product from the PTMApp web that Chuck talked about that shows you those 2-year runoff volumes. This again is for the whole Red Lake River watershed. The data that's created, Sean was talking about file sizes yesterday. When you're done running PTMApp on the desktop for the Red Lake River, the file size was about 100 gigabytes of data. It's a huge amount of data that's being created. Remember, we're doing that, all those raster calculations underneath, so it's a huge amount of data. But this graphic is showing you the runoff volumes for the Red Lake River using the curve number method. The dark blue areas are the areas with the highest runoff volume. Why do you care about that? Well, maybe you have a stream bank downstream that you're working on and you want to get a relative sense upstream of where the volume's coming from. This might be a useful tool to helping you target where to put those practices. And then the next piece that I want to talk about are the best management practices. You're going to hear a common theme from what you heard yesterday with Dr. Tomer. Essentially what we're doing here is using various factors, various design criteria, various landscape features to get a sense of where practices should go on the landscape. What's different than what you heard yesterday is we put all of those practices and more that Dr. Tomer was talking about into what we call a treatment group. So if you go to the documentation, you'll be able to map NRCS or MDA practices to the treatment group. Why did we do that? Because what's different is we're actually estimating the benefit expressed as removal efficiency of those practices once we identify in the landscape where they can be placed. So we didn't want to have to write, there's like 50-some practice types. We didn't want to have to write pollutant removal equations for each one of those practice types. So that's why we put them into treatment groups. Those treatment groups behave similarly, so take storage. I don't care if it's a wetland storage basin, if it's an impoundment, if it's a pond, it basically all removes pollutant or the sediment by deposition. So that's why we clump them into treatment groups. One of the things we do is we include the field office technical guide in the criteria in setting those practices. We do estimate the actual load reduction of each of those practices on the landscape that come out of the feasibility analysis or come out of the analysis essentially. And one of the cool things I think is we are actually able to estimate the combined benefits of multiple practices placed in a watershed at those downstream sub-watershed and watershed points. So again, the combined benefits of those practices at those red points that I showed you on the map yesterday. And we do include a feature where you can estimate cost. And we typically use the equip payments for that. We realize that's maybe not the best information to use to estimate the cost of those practices, but the user can change that. Rather than get into a debate about what those costs are, we just provided the user the option to make this decision what they want to use. I was an ecologist before I was an engineer, and I hated equations, so I'm not going to go over these equations for you. The message that I want to leave to you and leave with you is that one of the things that's unique about what we're doing is that we're actually estimating the load reduction in those practices, and we're not making it static, so it's variable. We're using information from the literature, and we're using information about, for example, how much water a practice actually sees compared to how much it can treat to adjust its removal efficiency. So just remember that as a take-home from PTMApp. If you have a really small BMP that sees a lot of water, it's not going to be very effective at treating that. So there's some equations in PTMApp. Drew did this, smart guy. He was the one that was kind enough to come up with this approach. Because we're keeping track of hydrology, we can actually do this. And so this is what the equations kind of look like when you plot them up. And on the x-axis is the treatment ratio. On the y-axis is the actual percent reduction at the best management practice. The different lines are this issue of uncertainty that we talked about yesterday. So these different lines represent different treatment efficiencies based on literature values. We have a minimum efficiency, a maximum efficiency, the median, and the quartiles. So this allows you, if you want to do sensitivity analysis, what if those practices don't perform as I expect? What is the outcome? This addresses some of the issues related to uncertainty. And I mentioned that we could do essentially an evaluation of practices in combination in the landscape. Again, I don't want to go through the math for you if you're really interested. We can talk through that with you, but I think the important take-home message is that we can evaluate and estimate the benefits of multiple practices on a landscape placed at a single time, whether those practices are in series, one above each other, so the upstream one drains to the downstream one, whether they're in parallel, so they don't directly drain to each other, but the flow joins downstream, or whether they're in both series and parallel. Not unlike what Dr. Tomer showed you yesterday, one of the products is a map, a series of maps, geospatial products, again, where the treatment efficiencies are kept track of, that can be used to help people figure out where are my best opportunities in terms of solely pollutant reduction for practices. What I'm showing you here is a graph of the Root River watershed. I think the total drainage area is about 2,500 square miles. About 1,700 of that, as I recall, is actually direct drainage to the root, or drains through the Root River. And I'm showing you the results of the source reduction treatment group. What is source reduction? Nutrient management plans, residue management kinds of practices. And again, we're estimating the value of this in terms of the load reduction at all of those red points on the landscape. Just so you let you know, when we ran this treatment train approach where we looked at all these practices, Drew ran like 1,500 practices through. The computer chugged for about 5 weeks, as I recall, steady. So it takes a lot of time. And that's one of the downfalls of what we're doing here with PTMApp, is it can take a lot of time to process that data. That's kind of the final step that takes the most time. So I want to show you some examples of how this is being used. And I give credit to this to Drew Kessler. He was the one that did this for the Sauk River. What I'm showing you here, I believe, is Adley Creek. I can never remember. Anyway, I want to step through some of the products that are coming from this and how it's being used. The issue in the Sauk River Watershed District is they have a RAS. They have a RAS strategy. What are they doing? They're trying to refine that. They're trying to get more specificity. Where do I put the practices? What practices? What benefits do I get? So one of the products that's useful to them that they may look at when they're trying to decide where to put practices is, where's the junk coming from? Now remember, we're able to, in PTMApp, keep track of where it comes from, but also where it goes to. This graphic shows you the sediment contributions downstream, essentially at the terminus of the drainage area, which is this blue line, to the Sauk River. Those darker areas are areas where the highest sediment contribution comes from and actually reaches that particular location. It's an estimate. Remember, it's for planning. The other thing that would be of interest to them is, where do I put the practices? When you first run PTMApp, just like Dr. Tomer's application that he's developed, you get information about where potential practices could go. In this case, they're treatment groups. That's what I'm showing you here on this particular graphic. And so those areas on the lower left-hand side are opportunities for source reduction, biofiltration, storage, and the like. All right, so now I know where it comes from. I have some estimate of the locations to place it. I have some idea of the best practices. I can take that fine-scaled information and I can add it up in essence within those catchments. So I know how many practices might go in the individual catchments, and I know or have some information. I shouldn't say no. As a modeler, we don't know anything. We estimate everything. But we have an estimate, if you wish, of the potential cost or the probable cost of implementing those practices in those catchments, in those particular catchments. That's what I'm showing you here on the screen. Those darker areas are areas showing the greatest bang for the buck, if you wish, in terms of the sediment reduction at the outlet of this drainage area for those individual areas. So now I know not only where are the practices, where is it coming from, but give me some idea of the cost. When you run any tool or you're doing scenarios from PTMApp, you get more practices than you can physically implement. I mean, you saw the previous graphic, source reductions all over the place. This is where you need local knowledge. This is where you need to work with the local folks that are actually implementing these practices. Where are we going to actually target practices to place on the landscape? You're not going to do all of them, so someone needs to build or work with them to develop an implementation approach. And that's what I'm showing you here is, locally, they wanted to implement in the lower part of the watershed. And so these are their targeted locations for practices. I'm going to switch now and show you one watershed, one plan example. Chuck mentioned that when you download the information from the website in PTMApp, you get basically a geodatabase with a bunch of information in it. That information is useful for helping you describe your watershed. If you're a soil and water conservation district, you don't have a lot of ability sometimes to use this information. So what we've done is pre-packaged data so they don't have to go hunting for it. One of the simple things that's in there is just where are the streams, where are the impaired stream reaches, and the like that you can use to describe your watershed. When you do a one watershed, one plan, you're supposed to focus on specific resources. Some of the data in that geodatabase will help you do that. Whether it's an impaired stream reach layer, or in this case, whether it's related to drinking water, what I'm showing you is private well locations and their nitrate concentrations. And also in the upper part of this graph, what I'm showing you, this area here is a drinking water, source water drinking management area. It helps you identify where those are if you're interested in, say, as a priority, groundwater for drinking sources. Not unlike I just showed you, this happens to be the South Fork of the Root River, is the first step could be prioritize where I put my practices. This is the source load map that I showed you previously. Darker areas are areas on the landscape where that ranked now, where that sediment actually reaches the outlet. Again, I have the practice analysis, the BMP siting analysis or locational analysis, and that's what I'm showing you here, is these different colored areas are different treatment groups that are technically feasible. How often do we implement practices based solely on technical feasibility? Almost never. So here again, you need landowner input ultimately at the end of the day, but I just want to point out that there's a lot of practices there. We're not going to implement all of those. But we can get some sense of where the investment is best. That's what I'm showing you here. So this is information about the unit load reductions per dollar. Again, reaching the core point, reaching this most downstream location. If you had put red dots out here in other locations, you could also get that same information for those other locations. At the end of the day, you're not going to implement all those practices. You have to develop an implementation approach. One way you could do that is you could use that BMP efficiency information and say, you know what, I want to implement those practices that are in the top 25% in terms of their load reduction at the outlet. So you could then take that master list of practices, if you wish, or that the earlier step that I showed you where it's identifying all those things on the landscape and whittle them down using some criteria to the few that you actually want to evaluate in combination. That's what I'm showing you here. Ultimately, at the end of the day, again, there's a little piece out there called landowner willingness, landowner acceptance that has to be brought into play. So one of the things you can do in PTMApp, if you wish, is say you have some external data about willing landowner, maybe you want to bring in the crop productivity index, maybe you want to bring in some other data to use that to screen down your practices. You can bring that in and use that to essentially eliminate or to focus on specific areas if you wish. That's what these red circles are. Maybe those are areas where you know you have willing landowners to implement those practices. And at the end of the day, you can take all those practices, you can run it through the treatment train approach in PTMApp, and get estimates of the load reductions and the yield reductions on an annual average basis for sediment, total phosphorus, and total nitrogen at multiple spatial scales. And that's what this table represents in the colors on this graphic. So those practices are spread all over, but when I run PTMApp and get the products out of it, I'm able to get sediment and yield reductions, evaluating those practices in combination at, again, multiple spatial scales. Not only at this point, but if I put points in other locations, I can tell you, or, geez, I did it again, didn't I? I can estimate the load reductions at a different spatial scale, at a smaller spatial scale. How am I doing on time, Mr. Moderator? I got to leave 10 for Henry, so. I'm going to briefly touch on a couple other topics for you to show examples that are in progress or have been used. I feel like some days we get into this discussion about my widget's the best widget, use my widget, okay? The reality is most of the things you've heard here can work together complementary. So Whether it's HSPF or whether it's SWOT or whether it's the results from PTMApp, you can combine that with zonation. So what I'm showing you here is the source assessment map, essentially the load map. And you can take that, in fact they did that in the CROW, and they gave it to Paul Rodonsky. Is Paul here somewhere? I know he's speaking later today. Okay, you can give it to Paul, and he can use that in the zonation process. So again, this is complementing other techniques. Similarly, Paul was kind enough the other day to send me this map. I didn't tell him I was going to use this, so credit goes to Paul. But this is the results from the zonation. This is the conservation priority location. How does this work with PTMApp? Those red areas on there are the results. Those are the hot spots for priorities. I can then take this to use that to screen my practices, to say, I want to preferentially put practices in those areas because those are my priorities. Then I can run that back through PTMApp, and I can see what the benefits of those practices are downstream. HSPF, SWOT, what Dr. Tomer showed you yesterday in terms of the siting for the practices, they can all work together. And here's an example of how that's been done for the Lake of the Woods watershed. This is a graphic that shows the results from PTMApp. These colored areas are potential practice locations that came from PTMApp. We worked with the local people to say, what do you really want to implement? We used that to develop 3 implementation approaches. We took those results from PTMApp, practices on the landscape. We plugged them back into HSPF, figured out how to simulate them in HSPF, and then what comes out of it is what are the load reductions at the lake. So the tools work together. They're complementary. You can use PTMApp with other geospatial data. One of the critical things in the root river is where does the water go? So when you're citing practices, you're deciding where to implement, and you're looking at those loads, how do you know where to focus? Jeff Green from the DNR was kind enough to work with us on this method. I'm not going to go into the details. What I'm going to tell you is that we developed what's called a predominant hydrologic influence map. That's what I'm showing you here. These different colored areas based on karst formations, based on depth of bedrock, represent at the catchment scale the likelihood that water goes to a certain place, whether it's surface water, groundwater, or both. You can then lay that on top of the PTMApp source information. The green areas are areas that are the greatest sediment loads leaving the landscape. This then gives you some sense by combining this information of where does that load maybe go? And I say maybe go because it's incredibly complex in terms of the actual hydrologic mechanism. So those areas in this graphic, for example, that are dark brown and have a green circle, those are areas with high sediment load that go to surface water. Those areas with kind of the gray background and the green circles go to groundwater. And you can do the same thing with your BMP analysis. To give you some relative sense of where the benefits might accrue, to what resource might they accrue, surface water, groundwater, or both. And so to close out, like anything, there's limitations to what we're doing. If anyone tells you there's no limitations to what they're doing, then they're a liar. Okay? There's limitations to everything we do. One of our limitations is the desktop processing times when we get to the large watershed. So if you're trying to process 1,000 square miles doing treatment trains, it takes a long time. That's kind of a problem. We have some techniques to speed that up, but we haven't implemented those yet. Okay. One of the problems, so as a classic modeler, I would tell you one of the problems is we're pushing the scale of the data. You heard Sean talk about scale yesterday. But we're doing this computation at a very fine scale. We really don't have the land use data at that same 3-meter raster scale. So in a way, we're breaking kind of a fundamental rule of modeling. Dr. Steffen would have admonished me at the university for doing this, telling you that you're limited by the scale of your data in terms of what you can do. So, sorry, Dr. Steffen, I didn't listen or learn very well. We still need more validation. Any model needs validation. Any product needs validation. Okay? Again, basic take-home message. Check to see how well it's working. Currently, we are not including existing practices on the landscape. However, if you have information, you have a geospatial file, you have a shape file of that, you can put that into PTMApp desktop when you're processing the data. We have issues related to the forms of nitrogen and phosphorus. We're only doing TN, we're only doing TP. Especially on nitrogen, we're not speciating nitrogen. That's an issue, really, because the behavior of that, whether it's inorganic or organic, is different in the landscape, in the environment. We don't have channel sediment yet, okay? We want to get there, and we really don't have any hydrologic routing yet. There are valid concerns. How many people trust models? Some do, some don't, right? But that's an issue. We need to be realistic and credible when we communicate the results about what we're actually showing people and what we're actually saying. Relying on an absolute prediction is always an issue, especially if you haven't calibrated and you haven't verified any model. What we need to change the discussion to is the absolute prediction correct, or is the decision correct? The decision ultimately is, are these practices reasonably in the right location with the expected amount of benefit? Are we making the right implementation decision? We have landowner issues related to privacy with these data. Specifically, the farmers are concerned, as are the soil and water conservation districts, about this information being misused. Now you have someone like me that says, hey, a practice should go here on your land, and that can be used for a variety of purposes, some not toward the end goal, which is actual implementation. And that results sometimes in a shift of the burden of the proof to the landowner to prove to someone else, why aren't you doing this? So you need to be aware of that. Ultimately, at the end of the day, what we're after is an open discussion and debate. So one of the things I want to leave you with is, it's not about the widget. It's not about whether this is the right tool without the discussion about what is your goal, what is your objective, what are you trying to accomplish. So I've actually done this. I've taken a hammer and driven a screw, and it works, right? But usually when you get close to the wood, it doesn't turn out so pretty. So make sure you're asking yourself, whenever you do this at the end of the day, what am I trying to accomplish? What are the goals and objectives? Chuck said this is for the local practitioner. That was our goal, is to get hands in the information of the local practitioner. We do have some next steps related to Bowser. You can talk to Melissa about that if you want to do it. We are working on other things, and I've mentioned that. If you want more information, then you can go to the website. Again, we've tried to be intellectually honest about this. All of the documentation is on the website. You can download the desktop, and ultimately you can get to the web app there as well. So Henry, hopefully I didn't take all your time.
Oh, it's okay. It was your show.
Thank you, Mo. Where did you... Is this the right thing? Okay. I'm just going to go through a quick example of how to use some of these models and integrate them into natural resource and the prioritization process that we're trying to do at a watershed scale. It fits in the 10-year cycle really in where those stars are. And I wanted to also say that the base data that you showed that goes into PTMApp really gets us, as Mark said too, the water resource characterization box. And I'm not going to go through this because of time, but we have a lot of data from the LiDAR already derived that people can use. The condition DMs, all the flow accumulation lines, everything is there in the Red River Basin, available on the web and available for download. We've also done things like, where are all the existing depressions on the landscape? What is their volume? What is their footprint? What is their drainage area? We look for water storage. Where's the road depressions? We've raised all the roads going east-west. Where could we store water on the landscape? All those things are available, and people are starting to use them. And we're just going to go to this. I wanted to also frame this in, what is the conservation delivery system that's out there? We've been talking a lot about models and talking about who's actually implementing things. Landowners are who does implementation. And 78% of the land in the state of Minnesota is owned by private people, private landowners. And we have a lot of money from NRCS, Bowser, other agencies also passing through to landowners. Local governments help with that, and agencies
provide technical support, planning, through oversight and regulation. But much of the stuff, and Chuck talked about this, Mark talked about this, Dr. Toller talked about it, landowners are making the decisions. So we've been hearing a lot about, my perspective on this is how do we leverage all this great information we have on water quality, all the data, tools, and models, but instead of just for water quality, how do we leverage them for hydrology and for habitat? And we've gone through yesterday 6 hours of this, and finally in the last 15 minutes, Dave Wall talked about habitat. And if he said it 2 times, I'm going to say it at least 3 times here. But from my perspective, this is about how do we get habitat on the ground, improve our hydrology, as long as we're doing all this water quality work. And we have to keep in mind that most of the actions, the list of actions we can do is quite short, and we have to rely on willing landowners. Dr. Toner had 3 or 4 categories. The PTMApp has 6 categories. Those are the types of things we can do on the ground. So if we have a goal overall, and I'm going to Red Lake, of where we're doing one watershed, one plan, of improving watershed health, really the bottom line there is to protect and restore habitats and hydrology from my perspective. This is really bad. How are you doing this, Mark? And in simplified form, the habitats out there include wetlands, grasslands, brushlands. Yes, there are things called brushlands. There's a state plan for them and their restoration. There's riparian lands, forests, watercourses, and lakes. And in the Red Lake, our priority habitats are wetlands, grasslands, riparian lands, and watercourses. And here's the example of how we bring this all together. So the PTMApp gives me where is the sediment coming from and going to the outlet of the watershed. The Minnesota Prairie Plan, overlay that, you get the priority zones for wetland and grassland restoration in the watershed. At the watershed scale, our wetland and grassland restoration and protection priorities are there. We can quantify how many acres we want back and how many acres we want to protect. Within that zone, if we zoom in, this is where the PTMApp is telling me storage is a good best management practice. The red areas are high priority, the green are lower priority. So I know where the sediment's coming from, I know where the storage is a good BMP. I can zoom into a 9 square mile area. That red area, it's kind of in the top center, is a high priority for storage, and it's a high sediment loading area. Well, that's what the landscape looks like. Not a lot of storage there right now. We created some data which is the drained wetland basin inventory based on LIDAR. There's where your drained wetland basins are. I know their depth, I know their volume, and I know their drainage areas. So we can give these maps to local governments to say, here's where you need to go and do wetland restoration, or here's at least your priorities. And what some of the local governments are doing is overlaying this information with the parcel data that they have and doing a mail merge and sending letters to all the people in those areas that say, we have opportunities to restore wetlands, there's these programs, come and talk to us. So it's a direct application of prioritizing and then really targeting and then actually marketing where we try and get conservation put on the ground. And this is an example of a DEM that's been gone through this drained wetland process. The one on the left is your normal, raw, or conditioned DEM, I think in this case. On the left-hand side, you see a road, and you can see the drainage lines. The right-hand side is where we've smoothed the roads, gotten rid of them. We've smoothed the drainage lines, or at least the small ones. Then we can identify where the drain basins are. We put a plug in all the drained areas. We put that back into the original DEM to maintain the watershed's integrity, and we get the drain basins. So that's just one product we've created. This is the HSPF data on runoff coefficients, volume of water per unit rainfall. Again, another hydrology measure that I can work with my drain basins to go, where are the best places to put water storage? Supplements PTMApp. I know there's a SWOT model for this watershed. That's probably got similar data. And then we also have a HEC HMS model. And in this slide, it's showing you the blue areas are the highest priority areas for water storage to reduce peak flows at Crookston. Again, overlay the drain basins in those blue areas, great places to prioritize wetland restoration for flood damage reduction. So switching gears from this example, we're also working up some data because of the drain wetland basin for wildlife management areas. This is a WMA. Here's that drain basin layer. Identify where there's opportunities to restore wetlands on WMAs. And we can go to a watershed and say, look, here is a WMA where we have an opportunity to store an additional 1,400 acre-feet of water. Do you want to partner with us to do a project? Often, when we're talking about this with WMAs, that means we're going to have to expand the boundary of the WMA because most of the wetlands have been restored up to the boundary. And here's another example for another WMA. There's your map of all the restorable drain basins, and then we can, again, generate data, quantified data, the size, the drainage area, how much runoff those will retain. And then lastly, the one tool we created was priority watercourse inlets. Stream power index is available for the basin, but you get all these lines and they're messy maps. You got to zoom in close or else it's just this network of lines. We said, instead of doing it that way, let's take drainage areas that are, say, 2 square miles to 10 square miles. Where are the inlets to them, and what are the priority inlets to look for doing things like side inlet controls? So this is a ditch, and then the color coding is lines that have more stream power to less stream power categorized. And I've run out of time. These tools are all available. I also want to mention the NRCS engineering tools that are available. Those have been around for 4 or 5 years. You can do a lot of this work in those too. That's where the people are building WASCOP using the NRCS tools. And yeah, that's about it. We have all this data and tools, and it's time to get to, we're at the crossroads of strategy and implementation, and how do we get the implementation is the bottom line.
So before you leave, so your current presentation, and where could people get all of those available?
So the question is, where can you get all those available tools? Contact me. The NRCS tools are on the MinGeo website, and there's a set of videos to them and how they are used. The drain wetland tool is available for folks to use in our GIS. So just get a hold of me for those two.